First, I'd like to introduce the METEOR project, which enabled the creation of this video. METEOR stands for Modelling Exposure Through Earth Observation Routines and was funded by the UK Space Agency through their International Partnership Programme as part of the Global Challenges Research Fund. The METEOR project aims to develop innovative application of Earth observation technologies to improve understanding of exposure. Natural hazards have had escalating impacts, which are contributed to by an increasing exposure of population and assets. However, a major challenge when making disaster risk management decisions can be a poor understanding of the distribution and character of exposure. Robust quantitative methods are required to justify these decisions, and in this project, we are looking at the use of Earth observation technologies within that context. Within the METEOR project, there is also the aim to share knowledge. This video is produced as a part of a series of educational videos to enable the use of METEOR products and data.
Almost in a sampling capacity. All right, now for the next section. We've gone through an introduction to exposure data, so hopefully you have an understanding of what it is, what we're talking about, what we're not talking about. A very basic idea of the elements that go into putting together an exposure data set. And now trying to answer the question, is it any good? Is it useful for my purpose? Not an easy question to answer. I think you need the background in terms of the first two sections that we talked about here to be able to truly understand exposure data. But I'll be trying to talk through some more tools to do that. Again, going through the levels of exposure data in a little more detail. Talking about the resolution and scale of the data and the hazard with respect to the hazard. Harping on the key parameters a little bit more. Talking about metadata. We got a whole nother section on metadata that our analysts that put together the format for that in this project will be doing. Talking about validation just a little bit and understanding the limitations of the data. So I want to go back to to some research that we did on this project, which was for the Los Angeles area. Again, here are the 5 levels of exposure data. We had an opportunity because of our history here in Los Angeles since the Northridge earthquake to get our hands on a lot of different exposure databases that have been put together for various purposes. And that allowed us to do essentially all the way from a level 1 to a level 5 full probabilistic analysis of what the losses would be through time, given the different data sets. And that's because we do a lot of work here in California, so we had the engine to do that, so to speak, seismic program here, Seismicat, and we were able to wrestle the data into those formats and look at the difference. And what we found was quite illuminating. We want to spend too much time in putting these data together and correcting for bias and so on. We just wanted to sort of get it in there and see what the results were. And if we had taken a little bit more care, there might have been a little bit more convergence here in the results. But this was a thought exercise. It would have been ideal to do that if we had the different data sets in Nepal, where we do the significant earthquake risk, and maybe that's something that we can look at doing later. So level 1 data for Los Angeles, we actually downloaded from GEM's OpenQuake site. It's essentially was prepared, I believe, with Kishore Jaiswal as part of P366, essentially mapping their data into the GEM format. And here's what it looks like. I believe it was 60 arc seconds rather than 30 arc seconds, so maybe kilometer basis data. And here it is on mapped exposure. For level 2 data, we just took HAZUS data right out of the package. It's census data. We wanted to detrend for spatial resolution. So what we did was we ran everything at the 30 arc second level. So that means that we took that level 1 data, cut it into 4 pieces there, so that would be at the 15 arc second level. And for level 2 data, we took that and just that basic area weighted distribution to chop it up into those squares, so that it would be a 37 product. And here's what it looks like. You can see these large sort of flat areas where things are homogeneous. So for level 3 is we used work that we had done essentially looking at building exposure data sets, and by we I mean ImageCat in this case, developing a ITV, insurance to valuation, basically using EO data to do a smarter inference of what the replacement cost would be. So we did that as a level 3, and we also used, in that context, interpreted development patterns throughout the Los Angeles area to adjust the mapping schemes or structural classes of the buildings just a bit, not too much. And here's the level 3 data. So you can see it doesn't look too different than the level 2 data, but a little bit. A little more differentiation, particularly in the residential areas, these sort of orange swaths on the southern portion of the. So level 4 data was interesting. We got building footprint data that was released from the Microsoft virtual the Bing Microsoft data, essentially building footprints that have been released for the whole country. Now they're really looking at trying to do this type of work for the world. They need more training data to do that. But this is something that we can expect to be developed in probably the next 5 years. You'll start to see these building footprint data sets all over. So one would assume this would having that footprint would give you a better idea of the square footage, at least of how that building is represented on the ground, but then that has to be extruded to come up with the square footage of an entire area. So we use that for level 4, where the structural characteristics of level 4 is identical to what we have for level 3. So when you can see, this looks quite different than the level 2 or level 3, in that there's higher highs and lower lows. That goes down to, and that's it just does a better job at, in this case, capturing at the cell-based level where you've got green areas speckled throughout Los Angeles, where you've got areas where there's more building footprints, a higher density of building footprints throughout Los Angeles. And if you're familiar with the valley here, you can start to see major corridors, major development around particularly large boulevards and so forth. And this is the same area as was in that SAR photograph or SAR image I showed earlier. You can start to see some of the movie studios and so forth in some of these areas. So in that sense, there's a lot more different. Now, so for level 5, we used some research that we had done maybe 14 years ago, mapping the structural classes, well, not structural classes, the year built, the occupancy, and the fire codes that are in the tax assessor data for Los Angeles into vulnerability classes that could be used for Seismicat, essentially. For our program. Now, Seismicat is very much the way that the vulnerability is dependent on a lot of year of development or year of construction. So that was able to use that data, which was quite useful. So we actually, when we ran it, we did aggregate to a 500 meter area. And this looks like it's similar to the Microsoft Office level 4 data, but not. So here you have them all side by side again. The level 1 data for the entire area, not as much differentiation, a lot of low areas. The HAZAS data, which you're able to see things like the Wilshire Corridor and more areas of concentration in places like Pasadena. Level 3, which attenuates that a bit, looks like down in most cases. 4, where you start to really bring things into focus. Of course, that's because it's aggregated up from building specific footprints. And then level 5 too, which is an interesting almost mix between the level 2 and the level 4. At least that's what it looks like visually. So I want to take a step back now that I've kind of gone through those five levels and discussed them within the context of an actual project where we put together all those data sets for a concerted area. I want to talk about uncertainty, because we're really, one of the things that we were doing here of running these exposure data sets through the probabilistic analysis was because we really wanted to figure out what the uncertainty was associated with them, those data sets. If you put more effort into developing a level 5, is it going to pay off? That's really the question. And how much difference is it going to make? And if I'm worried about, if I'm only really worried about figuring out where I want to do something or where I need to focus, there's certain questions where you're just, it might not justify a huge effort, or maybe you don't have the funds to do a huge effort. How much is that going to impact the analysis that you're doing? So a lot of people really, when you start to talk to them about exposure data, talk about the law of large numbers. And the law of large numbers is, if I throw one dice, there's two dice here, but if I throw one die hundreds of times, the results will converge on a mean eventually, right? So here you've got the observed average, which will vary. But as you look here, it's you get to your 200th, 300th, 400th throw, it really starts to converge along a mean, based on the more times that you throw it. So the idea here is, if you sample 1,000 buildings, you're going to represent what happens on average pretty frequently. If you've got 200, well, you've got pretty close. If you're only going to sample 5, well, you might have the answer 5.6, right? But what happens when you've got completely, when you've got bias in your results, that the theoretical mean is nowhere near what you're dealing with in reality. And unfortunately, this type of bias happens all throughout the exposure development process. For example, if I've got the construction manuals from the Turner document there, I go through that and I figure out what it costs to build a fancy hotel in Dar es Salaam, and I apply that to residential construction, I'm going to be way off. And there's all sorts of problems like that bias the different components that are put together in exposure data set. And so some of the ones that are right off the bat, I've talked about them several times already. Replacement cost results are very sensitive to replacement cost. People per household, average dwelling size, exchange rates can really be one. Obviously, we didn't run into that in Los Angeles, but we've run into that in Africa before. And buildings are seldom actually sampled to get these results, and that can make a big difference. If you've got a theoretical way that you're thinking the buildings are going to be, rather than sending people out in the field to look at them and use that to with a stratified sampling approach. And the census data itself often has bias. So there's all these sort of problems that you can have. So the question is, if you're mapping what your loss is going to be over a return period, this is just a theoretical curve, what's going to be the difference between this level 1 and this level 5? Is it going to be a factor of 4? Is it going to be a factor of 8? Factor of 2? We really didn't know. And we felt as if no one had really studied this problem significantly, gone through an entire probabilistic analysis with various exposure data sets to see what those results would be and to see how much error is actually can be attributed to the exposure data itself, simply because in any given exposure project, you use the best data you have, right? Of course, if I've got level 5 data at my disposal and enough budget, I'm going to process that and use it rather than the stuff that's off the shelf to look at my hazard. So we thought, at least for this one hazard, earthquake, we would detrend spatially and analyze the stuff at the 30 arcsecond level and run this to see how much error that we got that was just associated with those 5 different ways of putting the data, which is just what I said. And these are the results that we got. So these are the losses in US dollars on the y-axis here, the return period. And the level 5 here is on the bottom, and the level 4 here is on the top. And then you have got the level 2 under level 4, and level 3 in the middle, and then level 1 under level 3. So it's not monotonically increasing. It's not converging as you have more spatially high resolution data incorporated. So this was really quite a finding. The distribution, I think, alone is quite meaningful. So what we decided to do was take a random sample of buildings here in Los Angeles, and I think we had something like 600 buildings, and run them through as if they were records in these various exposure data sets to see what was really the result of what was really impacting the results most. And what we found was it was the area associated with buildings and the replacement cost associated with buildings. You see this level 5 here is down on the bottom. That's the tax assessor data in Los Angeles. Tax assessor data in Los Angeles doesn't have every building. And they don't have every hallway, right? They don't have every garage. There's a lot of building area that they don't include, and there are some systematic reasons why in Los Angeles the assessed value of homes tends to be lower than one would expect. This level 4 here at the top, turns out that's the Microsoft Office building footprints. They squared off the buildings, and when we extrapolated that based on height, that tended to give us way more square footage than we were finding when we went in and looked more carefully at buildings. Turns out buildings aren't cubes. The second floors and third floors often have less building area, and the buildings tended to sort of overestimate, particularly when they started to look at garage areas. So when we detrended for that, what we found is level 2, 3, and 4 were right on top of each other, which makes sense because the damage, the vulnerability there was assessed almost completely from the HAZOS data with just a little bit of adjustments made by our engineers based on the remote sensing data. And we see level 2 is a little bit above level 3 and 4, level 3 and 4 having the adjustments that we made, but they're all basically right on top of each other. and the level 1 and level 5 have different vulnerability assessments that have a different curve essentially. So what that tells us is that there's really very key things that you need to really focus on when you're developing these exposure data sets. And persons per household, living area per household, rebuilding cost, and exchange rates are all things where will exactly proportionally impact your results. So if you think that there's one person per household and it turns out that there's 2 people per household, you'll be high by 100%. That will affect your results by 100%. If you've got the persons per household varying throughout your country substantially based on the way people live, so that it's 9 people per household in the north part of the country and 3 people per household in the southern part of the country, your results are going to be very, very off if you take a mean, for example. And the same is with living area per household. If people have a lot more living area in rural areas where they're less cramped, and that's not reflected in the data and your estimates, that's going to impact your results proportionally, and rebuilding costs and exchange rates similarly. So this is some results for exchange rates to the dollar for a country we were working in Africa. And you can see it went to being tied for 100 units per dollar in 2008 to 700 in 2000, I think 16 or 17 it was. So that's a factor of 7. If you've got the wrong exchange rate, you're going to be off by a factor of 7 if you chose 2011 rather than 2016. So you have to very watch for these things and adjust for them. All right, more understanding exposure data. All right, so let's take a look at resolution and scale of impact given the hazard once again. So I think I introduced this problem already. This is the, I don't know if it's a province or administrative unit in Beijing, and the problem of how does that correspond to flood hazard in Beijing. So you go back to the original data, and if you want to try to figure out what the exposure that you have in a given area correlates with those flood hazards, it's not going to, you're going to need to figure out a way to essentially localize that data. And you've got, here are the 2 data sets that I had introduced, the classified image and then the classified aggregated up. So that data that's aggregated up is going to be more accurate in terms of the number of building estimates, the distribution of buildings, because obviously if you're trying to distribute buildings at this tiny speckled level, you're going to barely have a building to distribute, for example. And because of essentially the law of large numbers, it's going to give you a higher accurate for this aggregated area. But the image on the right is going to have higher resolution. And I think we've got some examples here. Here, if you look at some of these mixed pixel effects and this middle circle and this big large strange section on the left, throughout this area, you can see just based on the shadows alone, these large apartment blocks and where they are throughout Beijing, where they've cropped up on the outer areas of town. And if you go to a classification of this data, you'll get something like this. And you can see where it's not typical development. For example, where those train tracks are, it might not come up with an answer, or it might come up with a wrong answer. It does an okay job of figuring out where your tall buildings are and identifying those in this deep red color. In some areas, you have just nothing that's classified. It couldn't figure out essentially what it was, but in some areas you've got these speckles of yellow and so forth. So in the trend, it seems to be okay. And if you aggregate, and here we have the aggregated results for that. Now, if you're trying to count up buildings and assign vulnerability, this is the one that you're going to want to go with. If your purpose is to figure out where you could have flood impacts, that's a very different scenario. So if this is a river, you can see there's a river running through, and if you're trying to characterize the exposure, you might do a better job by having that higher resolution information and trying to use the amount of area that intersects your flooded area estimate and not use the gridded data that would be more accurate. But then you have the problem of what's the legacy of that data? Are people going to understand it as you start to distribute it? So there's a fine sort of trade-off between accuracy and resolution, where if you're using sort of the same data, the higher resolution could be less accurate, but in some cases be what you want to go with anyway. So all of this is getting us to the key point that it's important to understand the metadata here. It's important to understand the source of the data, the processing steps, the vintage of the data, key contacts, who you can talk to about how the data was put together if you've got any questions, particularly if if data that you're using was produced 5 years ago on another project and you got it and you've got a name that you can call and say, hey, you did this work in Tanzania 5 years ago. We would like to use some elements of this. What is it that you did? It's very handy to be able to do. Resolution of the data, not only of the final product that was developed, but the resolution of the input data into it, because you can take a census data set and interpolate it to a finer grid and use that for flood analysis, and you probably should if you're trying to find out what might happen in a different flood event. But passing that on, people are going to mistake that as a level 4 data set, for example. So trying to understand the metadata, that's why we've introduced this concept of the 5 different levels, for example, and understand, bake right in there into the ISO formatted metadata exactly what the methods were to put a given data set together, so that 5 years later you can take it and perhaps adjust it for inflation and population and use it again, or you'll know not to use it for building specific decisions if it was put together at the global level, for example. So we're going to have another entire session on understanding metadata, and Paul Amix will be leading that charge. So really, what we've tried to do in this the scope of this project is illuminate the process of how the data sets are put together, so that can be used in the context of decision making, and acknowledge the uncertainty, and really explore the uncertainty, and try to at least start to answer the question, how good is it? Now, validation. There's lots of things that you can do for validation, and they're all pretty time consuming. And they all take some expert analysis. You can go through and use a street view data to do your own independent assessment of the structural types, for example. You can do your own validation, send people out in the field to double check the mapping schemes and structural classification estimates. You can do as we did and make certain assumptions and come up with different methods and run multiple scenarios. That's what's been done here on the right as well. These are losses associated with a single building with many different assumptions in terms of what the structural classes are, to see how much error that actually introduces. And you can and should independently validate things like building area and replacement costs and people per household estimates that might really impact results. You can get confusion matrices and so on and so forth and calculate the error. But I would argue that the most important thing to do for validation is to look at the data and understand where it came from. That's going to give you, because of the complexity of the analysis required to come up with these exposure data sets, and the infeasibility of coming up with an error for every part of the chain and determining what the error is for the whole process without going through something as rigorous as we did for Los Angeles. Looking at the data, figuring out where it works, where it doesn't, how that might impact some of the results that are coming out of it, and understanding the entire process of putting together. Or maybe you have some expert that within your unit that can do all of the deep dive and then explain to the rest of you what's happened. It's probably more feasible. But really look at the data, understand what it is that you're dealing with, what the appropriate, and use that to determine what the appropriate decisions are that can be made. Understand the limitations. And this is an application. The PopGrid viewer was put together specifically to understand the limitations of the data by giving you multiple views of estimates of population, just for the purpose of understanding that uncertainty. Being able to visualize this uncertainty is going to be far more illustrative to people than having just a single number associated with error associated with the entire analysis, for example. Because of the larger law of large numbers, all four of these data sets, if you ask how accurate they are, if you're at the country level, you're going to get the answer probably that they're as accurate as the Nepalese census, because they probably all used the Nepal census as a starting point. How much does that vary on a cell by cell level? You can do the statistics and it might vary by as much as 200%. So understanding the base data, what the potential problems are that might be associated with base data, is the best way to understand the limitations of the decisions that you're trying to make. And yeah, trying to step back and figure out why you're doing what you're doing, and how you're going to use that answer. So, for example, if you're running a loss estimate for this region in this country, the replacement cost value itself may not mean a whole lot, but being able to understand that you have potentially 5,000 structures that would be severely impacted by a probable flood or earthquake, and that would result in displacement of X number of people, would probably be much more relevant information. So really keeping your attention on the question that you're trying to answer and how you can use these tools to answer your question, rather than letting the tools, the results of the tools, dictate how you think about the problem is important. So how do we price disruption? Because after all, what we're really trying to do here is characterize the risk associated with various natural hazards and how we might be able to mitigate that risk and how we might be able to prepare for that risk and ultimately reduce that risk. Putting a price on it can help in terms of making decisions such as should we spend government funds or international funds to strengthen these buildings here rather than there, or should we pay to strengthen the buildings rather than ensure food security in the near-term future. But ultimately, just looking at the price itself doesn't always illuminate the question that you're trying to answer. So that's really what's important, is to focus on what these events do to people, how it disrupts people's lives, and how you can use these risk results in order to prioritize doing something about it. Now, exactly what you're planning to do about it, that doesn't come from the tools itself. These tools will tell you perhaps where you should focus doing it, but you have to come up with the question first. The tools will help that. It's not a means to an end. Okay, so here are some examples of some things that we were able to do with our EO-based building exposure after the earthquake in Nepal very, very rapidly. We weren't working in Nepal. This did not have to do with the level 3 data sets. This was essentially a level 1 data set that we were able to put together quite rapidly. We estimated that the fatalities ranged from 9,000 to 22,000. Which my understanding is very close. We were able to estimate the number of collapsed buildings. We were able to use remote sensing data to find damage and use that to adjust the hazard, which at that point was not realistic. The estimate of the hazard was not realistic for the event. And ultimately, we were able to estimate where the displaced people were likely to be throughout the area. And we provided this information to UNICEF, and that was used for outreach purposes. So I would argue these are the kind of things that can be done with these data sets effectively without even drilling down to that monetary level. Now, after that event, trying to place a dollar figure for reconstruction, that is important. That's when you start to use that number, but you have to really be able to understand what those dollar figures mean in some of those areas where the construction is a little less formal. So, yes, questions that it does help answer. Is it cost effective to retrofit certain types of buildings regionally? Where should we focus our retrofitting efforts? Are building codes cost effective? And if so, where? What might happen after a 100-year flood, volcano, earthquake, or there's just been an earthquake? What are the likely impacts, and where are people affected the most? And where should we deploy resources? Those are the type of questions that we can answer with good exposure data and a proper risk process if it's been put together. Things that are unlikely to be able to answer with these type of regional exposure databases. Is it cost effective to retrofit this specific building? Which buildings fell down? Which homes are flooded? Exactly how many buildings fell down? It's all based on an estimate, dependent on the rule of large numbers. We try to correct for bias as much as we can during that process. I might tell you whether it's cost effective to retrofit this building if this building is a very typical URM, for example, in an area that's high hazard, and you've decided to have a program to mitigate or retrofit all of those types of buildings. But whether or not it's going to it's not going to allow you to make the determination in terms of what a building is without noting what type of that building it is by looking at it, right? If you don't have the structural type, it's not going to give you that additional information, and that's not what has gone into a lot of these exposure development process. If you're, for example, if you think of that that tree of all the possible structural classifications in a given grid cell, if you sample very, very diligently and bring all of them to the table, there's more branches than there are buildings to distribute, right? So when you have a building in an area, if that building is not something that you've identified as a high risk region, it's not appropriate to assume the structure based on that aggregate data. You have to look at specific buildings to make. All right, so that's my presentation. Thank you very much. You can reach me at ckh@imagecatinc.com. If you have questions, I'd love to hear from you. Thanks very much.